Hello, my name is Önder Soydal. This is the video presentation for the term project of the course EEE412 Microelectronics given by Professor Abdullah Talar at Bilkent University Electrical and Electronics Engineering Department. The aim of the project is to design a two-stage low-noise amplifier with Cree's MMIC process, draw its layout, and simulate. For this purpose, the Advanced Design Systems software was used. DC, S-parameter, and harmonic balance simulations were conducted for the tests. Here, the general structure of the amplifier is given. Both stages consist of single 2 by 100 micrometer GaN amps from Cree. RF signal propagates along the horizontal axis. Matching networks were constructed in order to match impedances conjugately for the optimal noise and gain performances. Furthermore, there exist three DC voltage supplies to bias the transistors. Requirements are as shown. The operation band is 6.175 GHz to 6.825 GHz. This corresponds to 10% fractional bandwidth. Input return loss should be better than 7 dB and output return loss should be better than 15 dB. Gain variation must be at most plus or minus 0.5 dB within the band. Smallest possible noise figure with the highest possible gain and linearity are aimed. At first, ideal and lumped components were used for the initial design. Then for the final design, real components from Cree's process design kit were used. Let's check ideal component design. Large signal models were used, and at first the transistors were biased at 50 mA per millimeter operation point. Later, it was observed that the bare transistor has a minimum possible noise figure of 2.44 dB at the band. Next, transistors were stabilized. Stabilization circuits were placed at the drain side, as any lossy component at the gate side would increase the noise figure. After stabilization, minimum possible noise figure increased to 2.6 dB at the band, and maximum possible gain was found to be around 15.5 dB for a single transistor at the band. In order to design matching circuits, noise and available gain circles were used. Since there will be a trade-off between the gain and noise figure, a point in between the center of noise and gain circles was matched to the center of the Smith chart. The output of the first stage and the input of the second stage were conjugately matched by interstage matching network for best power transmission in between. By using load mismatch circles, the output of the LNA was matched to 50 ohm for the highest gain. Overall, LNA schematic is given as following. There exist DC blocks and RF chokes at specific locations in order to isolate RF and DC paths. The gain for the ideal design was found as following. It can be seen that a typical gain of 25 dB with plus or minus 0.2 dB was achieved at the band. Furthermore, a wider band than required was obtained, and it corresponds to a fractional bandwidth of 32% instead of 10% required. Return loss were found to satisfy the requirements. Noise figure was found to be at most 4.5 dB within the band. OIP3 point is found to be at 17.5 dBm. After initial results, this design was reconstructed with real components from Cree's process design kit. The schematic for the design with real components is given here. The schematic includes all necessary connection components such as RF and DC pads, ground wires, T's for connecting three components in a node, capacitor connectors. Furthermore, additional transmission lines and curves were added to the design for layout placement purposes. In the light of all additional components, matching and biasing networks were updated. Furthermore, the bias point of the second stage was increased to 290 mA per millimeter for higher linearity. The layout is given here. The design is 2 mm by 4 mm and occupies 8 mm square. Ground signal ground probes are used for the RF signals. RF input is located at the left side and RF output is at the right hand side. DC pads are at the top of the design. After using real components, the gain variation is only plus or minus 0.125 dB, yet the gain decreased to 21.1 dB at the band. This is both because of the real components themselves and also because of the updates at the matching network. On the other hand, if the 23 dB peak at 5.2 GHz is further compensated, the design is promising to achieve 43% fractional bandwidth centered at 6 GHz. Return losses are as shown. Output return loss is 6 dB better than requirement. However, input return loss is around 2.5 dB at the band, which does not satisfy the requirements. Yet since the power at the input is small, this relatively poor input return loss can also be accepted. It was earlier mentioned that gain decreased and input return loss increased due to the updates at the matching networks. In return, noise figure at the band has been decreased by 1.2 decibel compared to the initial design. With real components, noise figure at the band is very flat and is below 3.3 dB. In comparison with 2.44 dB noise figure of a single Bayer transistor, 3.3 dB is a very good result. Furthermore, with the updates, the linearity has been improved. OIP 3 point has increased to 30 dBm. Thank you for listening.